Hey, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on scientific notation and significant figures. So we're going to be working with very large and very small numbers, and it turns out when you're doing so, it's more beneficial to round to a certain number of significant figures than it is to round to a certain number of decimal places. So rounding to a certain number of significant figures is similar to rounding to a certain number of decimal places. There are just some exceptions listed here, and they should become clear in our examples. So to better understand significant figures, we're going to take each of these three numbers in red and count the number of digits that are significant. So let's look at the first one. So these digits at the start, zeros at the start of the number, do not count as significant. So this first number has 1, 2, 3, 4 significant figures, 5, 6, 2, and 5. Let's look at the second one. So the third point says that we count digits before the decimal point. So this 1 and 0, they count as significant, as do all of the numbers after the decimal point. You do count zeros when they're between non-zero numbers. So this one actually has 6 significant figures. Now, if we look at the last number, it turns out all of its digits are significant except the last 0. So it has 5 significant figures. So hopefully you're realizing the only problems we run into are regarding zeros. So all the digits of a number are significant except zeros at the start or end of a number. Unfortunately, just to make things tricky, it turns out that there are cases when the zeros at the end of a number do count as significant. We'll go through those a little later in the video. So what we're going to do now is we are going to round each of those numbers in red to 3 significant figures. So we'll start with the first one. So we want to find a number that's very similar to our original number that only has 3 significant figures. So we actually do need to write the insignificant digits at the start of the number, otherwise our number will be vastly different to the original. So, 3 significant figures. Well, the 5 counts as significant, and so does the 6. So we need one more significant figure. So, do we write 2? Well, no, the one after it is 5 or more, so that means we raise the score just like when rounding to a certain number of decimal places. So this is the closest number to our original that has 3 significant figures. So let's look at the second one. So we want 3 significant figures. Once again, the digits before the decimal point count, so we write them. We need one more significant figure. So because we have a 0 here, 4 or less leave the mess, we don't round up. So let's look at the third number. We want to write a number that's very close with 3 significant figures. If I start writing the number, though 972, I've already used up my significant figures. So 972 is nowhere near this number, so what I need to do is I need to put zeros, insignificant zeros, instead of the 4 and the 1, and I still have the 0 at the end. So this number is very close to that one. So this is another example in which the zeros at the end of the number were insignificant, but sometimes you need to count them as significant. So to illustrate this, we're going to round 0.2399 to 3 significant figures. So once again, the 0 at the start does not count as significant. Now, what we do is we write the 2, and what we would normally need to do, because this fourth digit is a 9, we'd need to round this up to 0.240, right? If we didn't count this 0 at the end of the number as significant, we wouldn't be able to round to 3 significant figures. So when we're actually rounding and we need to count the 0 as significant, it is a significant digit. Sorry that that's confusing. But only count zeros at the end of a number as significant when you need to, when you're actually rounding. All right, let's now take a look at scientific notation. Okay, so if you're watching this video, you're a superstar, and this will probably be your bank balance one day. a lot of numbers there, and you can tell it's a really big number. So it turns out that if you include the digits after the decimal point, there are 12 digits. It would be really hard to remember all of them, and what would be the point? What we can do instead is just remember a few of the digits and get close enough. So let's say I only want to remember, the first few digits. Well, the first few digits are 1, 3, and then, I might round the 7 up to 8, right? But $138 is nowhere near this. What we do is we remember a few of the digits and also how many digits that there were. So it turns out there were 12 digits, but 10 before the decimal point. So this number, turns out, is about 1.38 billion. So in scientific notation, we'd actually write it as 1.38 times 10 to the power of 9. This tells us the first few digits of the number, and this tells us, are we in millions, billions, or whatever. So you can read this whole thing as 1.38 billion. That's close enough to this number. We don't need to remember all the digits. So that was a really large number. It turns out we can do it for really small numbers as well. So let's say we had this number in black. It might represent the length of something like a bacteria or something. It's not important that we remember every digit, but to make it easy on ourselves, we might write it in scientific notation, and it turns out it would be written like this. So please note, the power of -5 is actually a positive number. It's a very, very small number. It means 100,000th. So again, what we're doing is we're taking really large or really small numbers and making them easier to understand. So note, the way I wrote them in scientific notation, I started off with a few digits here, a number between 1 and 10, and I wrote it as 10 times 10 to the power of something. So this here in green is how we write numbers in scientific notation. So really, to change a number into scientific notation, we just have to figure out what goes in each box. So this is how you write a number in scientific notation. You just take the number and move the decimal point until the number's between 1 and 10, and then you write it in the first box. And then the number of places you move the decimal point goes in this second box. Original number was large, the number that goes in the box is positive, and if the original number was small, it's negative. Let's look at a few examples. Let's write this first one in scientific notation to 3 significant figures. So this is a whole number, so we can put a decimal point at the end without changing the number. So what I do is I move the decimal point until the number's between 1 and 10. So if I move it one spot, the number's not between 1 and 10. Still not. I keep going. If I move the decimal point here, the number becomes between 1 and 10. It becomes the number 9.73464. That's a number between 1 and 10, and that's what goes in the first box. So I take that and I times it by 10 to the power of something. Now, because I moved the decimal point 1, 2, 3, 4, 5 spots, I put a 5 in the power. Now, the original number was a large number. It was more than 1, so that means the number here should be positive. So this is actually the final answer for scientific notation, and to change to 3 significant figures, well, you know how to do that. It'd just be 9.73 times 10 to the power of 5. So let's look at the second example in blue. So I have a very small number this time. So I want to make the number between 1 and 10, so I need to move the decimal point 1, 2, 3, 4 spots, and it becomes 2.879. That goes in the first box. And then because I move the decimal point 4 spots, it would be times 10 to the power of 4. It's always times 10 to the power of something. Now, because this number was really small, the power is actually negative. Another way to look at it is if you move the decimal point left, then the power is positive, and if you move the decimal point right, the power is negative. Once again, note 10 to the power of -4 is not a negative number. We will do more on negative indices later. So if you put that on your calculator, you would get that. We haven't actually changed the number, we've just written it in an easier way to understand. Now we're not quite done because this actually has 4 significant figures, so to 3 significant figures, because this one is a 9, we round up. 5 or more raise the score. So to 3 significant figures, it's 2.88 times 10 to the power of minus 4. All right, we're just going to do one more example. Please pause and copy this down if you need. So let's do this question here. Andrew, attempting a maths problem, got the right answer, but didn't write it properly in scientific notation. What should he have written? So basically we're saying we need to write this number here. So the number, the value doesn't change, but it's written properly in scientific notation. So the reason this is not in proper scientific notation is this number here is not between 1 and 10. We need in scientific notation to have that because it makes numbers easier to compare. As an aside, if we wrote numbers in scientific notation like 137,422 times 10 to the power of 6, well, that sort of defeats the purpose of scientific notation. That would be hard to compare with a number like this. In fact, it turns out that these two are exactly the same number, but writing it like this is not helpful. It's not obvious that these two are equal just from looking at them. So that's why we always need to have this number here between 1 and 10. So how are we going to write this without changing the value of the number? So we need to move the decimal point 1 spot over. So we need to make this 1.2383. So to move a decimal point 1 spot to the left is the same as dividing by 10. Or if you like, by dividing 10 to the power of 1. So we have this number, which was 12.383, times 10 to the power of minus 3. Now, in this one, we can write it as 1.2383 times 10 to the power of minus 3 divide 10. And we know a bit about index laws, which you did last year. If we have two bases that are the same, 10, and we're dividing, we subtract the powers. So what we do is we leave our 1.2383, 10 to the power of negative 3, divide 10, you keep the same base, and you subtract the powers. Minus 3 minus 1 gives you minus 4. This is the exact same number as this, but it's written properly in scientific notation because it's a number between 1 and 10 now, and it's still times 10 to the power of something. Thank you so much for tuning into this video. The first 3 people from my class who reference this video and say Caramello Koala, you can have a Caramello Koala. Have a wonderful day. This has been the luckiest maths teacher in the world.